What are the main steps involved in conducting an exergy analysis? Have you ever wondered how energy is transformed and utilized in different systems? Understanding exergy analysis can provide clarity on this topic. Let's break down the main steps involved in conducting an exergy analysis, making it simple and straightforward. First, you need to define the system and process boundaries. This means identifying exactly what system you are analyzing and outlining its limits. This step is essential as it helps you focus on the energy and material flows that enter and exit the system. Next, subdivide the process into sections. This means breaking down the overall process into smaller parts. By doing this, you can examine each component's performance in detail, making the analysis more manageable. The third step is to select a reference environment. This reference state represents the surroundings with which your system interacts. It is typically defined by factors like ambient temperature, pressure, and chemical composition. Remember, exergy is always measured relative to this reference. Now, perform a conventional energy analysis. This involves calculating the energy inputs, outputs, and losses in your system using the first law of thermodynamics, which is all about energy conservation. This gives you a baseline understanding of how energy flows within your system. The fifth step is to calculate the exergy of all streams. Here, you need to determine the exergy content of all energy streams entering and leaving the system. Exergy quantifies the maximum useful work obtainable from these streams as they reach equilibrium with the reference environment. This includes looking at physical exergy, which is due to temperature and pressure differences, and chemical exergy, which is due to composition differences. Next, establish the exergy balance. This means applying the exergy balance to your system or each subsystem. The exergy balance states that the exergy input minus the exergy output equals the exergy destroyed plus any exergy losses. Unlike energy, exergy is not conserved because some is always destroyed in real processes. Then, determine exergy destruction and losses. Calculate how much exergy is destroyed within the system. This indicates inefficiencies and irreversibilities like friction, heat transfer across temperature differences, mixing, or chemical reactions. After that, calculate exergy efficiency. This is the ratio of useful exergy output to exergy input. It reflects how well the system converts available energy into useful work. Finally, interpret the results and identify improvement opportunities. Analyze the exergy destruction and efficiency results to find components or processes where improvements can reduce irreversibility and enhance overall system performance. Practical applications of exergy analysis are vast. They include optimizing power plants, heating and cooling systems, refrigeration cycles, and various industrial processes. By focusing on where and how exergy is destroyed, engineers can design systems that use energy more effectively, reduce waste, and improve sustainability. This method makes the principles of thermodynamics accessible by providing a clear measure of energy quality and potential work, beyond just energy quantity. It translates abstract thermodynamic laws into practical tools for improving real-world energy systems.